So welcome back. So this is our last talk for today, but first we have a small raffle. Who would like to win an iPhone? Okay, so if somebody is missing a black iPhone, we found one front desk. If two people show up, we will have to see. Okay, so next talk will be about IOMMU. Piotr, this is your stage.
Thank you.
Enjoy.
Okay, so I'm the last person between you and beer, and hopefully I will not bore you to death. The number is just coincidence. So, yeah. So I'm not expert in memory management in firmware. So this is like mostly my spare time work when I try to review patches which were very long abandoned, and I needed these patches to enable some additional security features, and would like to talk you a little bit about that. So we will talk about introduction, motivation, what we need for enabling AMD IOMMU, which is mostly ACPI, but I will not bore you with details of the structures, but just high level. And what's the implementation state and what we want to do with that. So who am I? I'm the founder and embedded system consultant in 3MDEP, embedded system consulting company based in Poland. We have a small team, like 20 people. We are mainly doing PC engines maintainership. We are very interested about security and updatability of the platforms. We are interested in learning about advanced hardware features, like virtualization I consider advanced, because not many so-called IBVs do this correctly. So yeah, so that's why I'm here. My motivation for this talk was fascination about what happened on the Zen hypervisor and various operating systems that grow around that ecosystem, which is CubesOS, OpenXT, and recently announced ViaOS, which are targeted for personal computing. So OpenXT is critical infrastructure, probably used by military guys. Automotive is ViaOS target. And then also I saw some customer requests on forum, on PC Engines forum, where they asked, they want to build virtualized firewalls to redirect like one Ethernet port to this virtual machine and then internally redirect traffic between other virtual machines. So that gives isolation for example, some web application which may be not secure. So if someone breaks into web application, will have hard time to get through VM and access other VMs to pound the machine. Also, NICs can be separated for different purposes because we have dedicated firewall systems like pfSense. We can just dedicate NIC for pfSense, and that's great thing about that. Proxmox can use those features. CoreOS is kind of system that may use virtualization, and as well like hypervisor type 2, which is KVM, for example, can utilize features exposed by ACPI tables, which define how to use IOMMU. So I would like to introduce you to some simple terminology. We have to know what's MMU, what's DMA, what's virtualization, and finally how it puts together into IOMMU. So MMU, this is just used for translating virtual addresses to physical addresses. Typically, we have, so it's mainly managed virtual memory. So it checks if we have correct access to this memory, and if not, then raise correct exceptions. It also controls cache behavior and do the bus arbitration if multiple accesses issued. It also has something called TLB, which caused recently quite a lot of problems. So it keeps the translation in the special cache, so this translation will be very fast. So that's in general. So DMA is something that we use to offload work from our CPU. So we program our DMA controller with some address, with some amount of data, and with some operation, which can be read or write. And then we can say we want to transfer this data from this place to this memory without interaction of CPU, or write or read. Yeah? So yeah, the steps are like, first we program the DMA controller, then we do the request to the I/O controller of a device, then we getting the transfer, and finally we finish the transfers, there is accepting, and then we get interrupt to the CPU that everything finished, and you can do something with this data that you wanted to read or write. Okay, so virtualization, we typically think about two types of virtualization. We have type 1, which is Zen, for example, and this means that we have kind of kernel, which is typically bare metal kernel, and after starting this kernel, we have like a virtual machine which manages creating other guests. In case of Zen, it's called DOM0, and guest called DOM-U. And in case of type 2 hypervisor, we just have a module in our operating system which help us create guest OSs of virtual machines. And of course, in type 2 situation, we can have other host processes that work with this kernel. And yeah, and IOMMU can help those hypervisors. There is something called IOTLB, which is just TLB for IO devices. So this picture shows more or less how the TLB works. So you can see that if CPU wants some memory, which here is called logical address, it can face two situations. Either it hits this address in TLB cache, which is fine because this is performance improvement. They will miss this translation to physical memory, and then things kind of complicate because then we have to do page walk and find this memory if it really exists and maintain that stuff. This is typically in cooperation with operating system. So TLB is mostly for normal memory access, and IOTLB is for devices. So finally, IOMMU. So IOMMU is MMU, but for IO devices. And what it gives us is it can give us hardware enforced memory protection. So that means that we can enforce that given device have access to given memory and not more. We can do virtual address translation for DMA. So in case of virtual machines, our guests are communicating with the outside world with help of hypervisor. And if this guest wants to do some DMA operation with the device, hypervisor is always involved. And that's bad because this is performance drop. So if we have virtual address translation, and we can program IOMMU to help in that, then hypervisor is offloaded and this can do that with high performance. Similar stuff is with page table sharing. Page table sharing is a technique which gives, for example, graphics performance. That means that we have some page tables, so we have some virtual address translation to physical address translation, and we just want to use the same virtual addresses for our processes and, let's say, graphic card. Yeah, and in that way, if we in both cases we can use the same virtual addresses, this simplified programming. And finally, we have PCI pass-through, which was most interesting for me so far, which is kind of ability to configure hardware in a way that one VM has complete control over this hardware. So it's even not visible from operating system then, if we configure that correctly. So what kind of problems IOMMU can solve? So one of the problems is DMA attack. So DMA attack happen at the point where CPU So first of all, how DMA starts. So CPU can issue some virtual address, then MMU checks protection, and if this process is allowed to access memory, then it gets access to the memory and can read or write. But then we want to do some DMA, like some DMA action, like read or write. So we configure the device to do this DMA action. There is normal flow that I described previously about the ACK and requests. But then this device, if device is kind of malicious, or we have buggy driver, or we have some other problems, it may happen that it accesses some arbitrary memory. And this is very bad situation, because this arbitrary memory can contain, for example, our private key or some data that we don't want to reveal. And because there is no MMU for device, then it's just no one can enforce that. For CPU, MMU takes care of enforcing the protection checks and correct translation. So because of that, we need IOMMU. So IOMMU, when correctly configured, will not allow device to access memory that is not that it should not. So yeah, as I said, it can be done by malicious device or buggy device drivers. Okay. So there are other features of IOMMU which can be helpful. For example, interrupt remapping and interrupt virtualization. So in this case, the situation is like, let's say we have guest that running on core 0, and of course guest can transition between many cores, like in multi-core system it happens a lot. And then if device issue interrupt, it goes through hypervisor, and then there is a need to figure out on which core guest is to deliver the interrupt. That causes something called inner processor interrupts. So processor just interrupt to interrupt correct between themselves. Let's say core 0 get the interrupt, but the VM is not there, so it looks for the VM on which core it is and delivers that interrupt to the machine. So thanks to the IOMMU, we have something like guest virtual AP table, which can help in redirecting interrupt just after arriving to correct place. So this is performance improvement. So I already told you about that. So virtual address translation, this is like kind of to not have overhead with the hypervisor handling DMA accesses from VM to the memory. Page table sharing is a virtual address for graphics and for normal process, and the PCI pass-through, you already know about that. So this is typical design of the AMD. It can have more than one IOMMU, and you can see that IOTLB is in the device. And this is kind of like just to visualize in your head how things look like. Where is the IOMMU, how it relates to the memory controller. So yeah, so that's the thing. So if the IO wants to access IO device wants to access DRAM, it has to get through IOMMU, of course, if it's enabled. So problem with IOMMU is that those components are very complex. Like the specs got like over 200 pages. It refers many other specs, and things getting complicated very fast. And doing that correctly is hard. And you can see in the net that many people complain that graphics pass-through doesn't work for me, and so on and so on. They want to play, for example, some games on Linux, and try to do PCI pass-through for the graphics card, and they cannot do that because ACPI tables are broken. And this is because there are so many features that even the manufacturers do not know how to program that. And this, of course, happen and propagate on IBVs, so independent BIOS vendors. And that's the example, because there are some basic features which are supported always, which are simple, like device virtual address to physical address translation, interrupt remapping, access permission checking. These are simple stuff. And then we have like a bunch of, like a 64-bit register, which enables various things which probably not work with all combinations. Yeah. So there are probably plenty of combinations that doesn't work. But there are some interesting features here. And I would like to tell you a little bit about that. Of course, we don't have time for, and this would be really boring to get through all those features. But the most important ones, so AMD claims that there are 28 software visible features in this IOMMU implementation. And yeah, so it's hard to identify those and even confirm that they work, but who cares? So very interesting feature, in my opinion, is SMI filter. So it can intercept unexpected SMIs. It can block some suspicious SMIs, which is good for security. Although I don't know how it exactly works yet because didn't dive deep enough in that. There are classic stuff like NX bit in page tables and access protection. And there is an interesting feature which is called MARC, Memory Address Routing and Control, which just scans through the IOMMU control to just improve the performance. But because, of course, IOMMU like cause drop in performance when configured. Okay, so yeah, if we disable IOMMU, this simply pass the traffic. But when we enable, we have like a kind of 3 things that every time we have to do. So we have to check permissions for any request from device to memory. And we have to translate addresses. We have to send those translated addresses to the system. And to achieve that goals, IOMMU use 3 tables, which is permission checks table, address translation table, and interrupter mapping table. And those tables are cached. And the problem with those is that user is responsible for invalidating those caches. So, and of course, this is no problem where we're facing cache issues on our platforms. And the nice thing about this IOMMU is that you can log plenty of events, and you can try to analyze that and debug that. Of course, this is kind of complex stuff and probably requires some manpower to do correctly. But for example, very demanding feature for PC engines, ECC, and you can log ECC events on low-level IOMMU registers. Okay, so what's important from the firmware developer perspective, from the implementation perspective? Of course, there is no way one system can utilize all features. It is recommended that this initialization will be performed by firmware before facing any operating system or hypervisor. So that's important that we have to do that early. Then the only way to describe this to there are 2 ways of describing that to the system, but most used is ACP11. There is device tree approach, but the problem with device tree is nobody using that, and that's but like nobody using device tree for configuring IOMMU. Everyone expose ACPI, and there are only ACPI drivers for configuring IOMMU. And yeah, and firmware must preserve or restore configuration between various power state transitions. Yeah, so also I talked with Ulf Risk about DMA attacks, and he said like that the configuration of IOMMU have to happen really early, even before PCI enumeration, because simply default parameters which you start with are incorrect and cause damage. If of course someone will be able to deploy malicious device to your system, for example, because this is most concern about this case. Okay. This is like first version of the slide had kind of screens from the spec that's showing the tables, but I just decided that this is completely useless, and you probably will, go sleep when you look at that. So I just try to visualize that. You can see here we have the main ACPI structure that we operate on is called IO virtualization reporting structure, is on the left side. And it can have two versions. There is ACPI version for the dynamic devices, and there is for other version, the version 1 for fixed devices. There is IV info structure. I don't want to get through to all the details. I even don't know all possible bits here, but just show you the structure. And the most important thing is IO virtualization block, which can contain two types of blocks. It's IO virtualization hardware definition and IO virtualization memory definition. And memory definitions are the one that very interesting for us from the protection perspective, because there we define who can do what. So what device have what range of accesses, what types of accesses, if this is read, write, and so on. And then we have IO virtualization hardware definition. This table defines set of devices that we have on our platform, which then can be redirected to our virtual machines to be directly used inside the guest. And that's mainly it about the ACPI. So what's the story about the implementation? So initial implementation was made by two people, Kiosti and Timothy, well known in coreboot community. So Kiosti implementation, like in 2016, relied mostly on Agesa. Agesa is kind of FSP for AMD. So he just relied on values returned by Agesa, and I will show you that this was not exactly correct, because Agesa just has a broken version of this table. Just don't care about correctly setting it up. And then there was kind of binary patching of this IVRS structure, which was also kind of not helping much for community. And for KVM, we have something called isolation domain. And this means in practice, all devices should have its own isolation domain to be able to be assigned to virtual machine. And the problem was that all devices were just in one isolation domain. So you either assign to VM all devices or not. So that was also the problem. And it was not stable across tributes. So Timothy implementation fixed it, like most of that. But the problem was like code was kind of convoluted, very nested. Quite a lot of hard-coded values which I cannot decode until now, because like I'm looking at it and there is like even 8 bits, each bit means something different, and I just wonder if I will break something if I change this bit or not, because it's not clear from the specification what it really does. But you know, I believe it's coming with the experience. And only the hardware definition type 10 was used, which means that it has some limitation, but I will not go down with that. If you want to, you can read the spec. Yeah, so, but kudos to those guys, because this started the work, and 3MDEP like in June started to continue that. We had this on to-do list for a long time, but they just didn't have time. And I recently tried to prepare that for motivate myself and prepare that for that conference. And finally, I was able to do the tests under Zen 4.8 and Debian with the long-term stable kernel. And yeah, so I'm still fixing bugs there, but something's working. So maybe a little bit about the implementation. It's very little, like this 9 file changes, 300 lines of code after simplification, because before simplification it was much more bloated. And we have simple thing that here. So this is coreboot paths, yeah, coreboot project paths. I just assume that everyone knows coreboot, but maybe not. This is not the case. So we just added some PCI IDs to make IOMMU detectable. In device tree, coreboot device tree, we enabled for PCNG's platform all the possible platforms 2, 3, 4, 5. We enabled IOMMU. Then we have to modify makefile to add the IOMMU driver. There is a simple IOMMU driver, which is not big deal in this situation, but the most important thing is in Node Bridge C, which is definition of IVRS ACPI table, and of course we need to modify initialization of the AGESA to make IOMMU use correct information and be enabled. Yeah, so how it is called? During boot, if someone familiar with the coreboot boot state machine, during boot we have a state which is called BUS write tables, and at this point we have a kind of call stack which we go through write tables, arch write tables, write ACPI table, and then finally we get through write ACPI tables for a given device, and we just have implementation for our device, which is our IOMMU, and then we can do some patching with the tables. So what we right now do, oh yeah, this is something what I want to show you. On the left side, there is a AGESA ACPI table, and you can see that it's much different from what I created. I can say that maybe with the pointer. Yeah, so you can see that this is our device structure. Each 8 bytes is one device, so we have like 6 devices just. This is not 6 entries, which is the platform is much bigger. It has Ethernet ports, it has MPCI ports, so it's much bigger than just those 6 devices. So obviously AMD didn't care enough about enabling that for various devices, and I understand that because this chip is used in various designs and they cannot predict all the possible designs. Yeah, but yeah, that didn't work. That caused hangs. If we enabled ACPI tables which were delivered by the vendor, this just didn't work. Just caused some additional problems, and it took time to figure out what is going on and why it's happened, because those hangs were kind of looking random. Yeah, but finally we have things fixed to the extent that that we can test something. And the question was, so this process took time, and there was not easy answer. Okay, how I will test that? Because then you are a firmware developer, and next day you have to test PCI pass-through from the hypervisor. And I learned about the Zen. And what we did, we just created kind of a development environment with Zen. So we booting Zen over Pixie. We're just creating PCI pass-through. Like this is bus 2 is our Ethernet card, like a middle port on APU2. I don't know if you're familiar with that platform. And we just passing it. We're just assigning it to be able to pass it through to the VM. Then we have to create correctly VM, and it will be assigned directly to the guest. And this is the proof. This is LSPCI from inside the guest machine, and it's showing our NIC controller, our NIC directly in the machine, and you can see it's different. It's different device in LSPCI in terms of topology, because this is not the host but the guest machine. And when we have that, we want to. What's important about that, we want to check if it's performed as it should. So we should have almost no penalty on between hardware test of performance and PCI pass-through. So, and this is definition of the Debian CFG that I used for creating virtual machine. So you can see here that there is a device that I pass through, and you need, of course, hardware virtualized guest. Yeah. Yeah. So these are information about the system that I tested. I also tested pfSense. I used iPerf to do the performance testing, and you can read more about that on our blog. This is results that I get. So so this is server side. This is inside VM, and you can see that this is gigabit Ethernet. So and you can see that I have like almost maximum. And unfortunately, I don't have screen for para-virtualized guest without hardware support, but the numbers are like 600 megabits per second. So it's like 50% increase in comparison to para-virtualized, and it's almost maximum possible by hardware. So that's very good. So then I wanted to prepare for that talk DMI attack presentation and show you that I can configure IOMMU to protect myself against DMA attacks. But the problem with that is it's quite complex to perform, and you need additional hardware and additional expertise. So I talked with Ulf. He luckily also have APU2 platform, and he checked some stuff, and he said like the best would be if you buy PCIe Screamer, and we already have that. It's waiting in our office for maybe next talk in next conference. And other things that were made in the area of DMI checking was that Google did fuzzing of Intel VTD, and they found some things in DMR because, okay, let's tell a little bit about the Intel VTD. So for AMD we have IVRS, ACPA table, and for VTD we have DMAR, DMAR. ACPA table, which doing exactly the same thing, but they of course have to invent different specification to make our life more complex. So Intel did the fuzzing, get some results, go to vendors, they fixed ACPA stuff, but they didn't reveal the fuzzing framework, and they didn't reveal much about the problems they found. They just wrote that there was something. Okay, so what's the current state? So we tested PCI pass-through for Debian and pfSense, and it works, at least based on performance numbers. And there were no longevity tests, so I cannot say you can take it to the production and use it. So that's something to do. We still have some small problems with hangs. It do not happen often. And I'm not sure if this is more a Zen problem or kind of something in my firmware. Yeah, still wondering about that. The problem is to realize that I have to enter Zen development area, which is kind of additional learning curve for me. And yeah, I don't know, maybe in the future I will provide something about that. And these random hangs, if someone want to go to the production, it's like you should not do that before testing and making sure it works for you. Yeah, so these are references that I use. So specification of IOMMU and AMD architecture. Okay, so so what we learned from that? First of all, vendors, like the supply chain is in a way that silicon vendor provides some reference implementation, then this reference implementation goes to the IBVs, which know more or less about the implementation, and they ship something, sometimes something modified to us, sometimes completely something not modified and not adjusted for our needs. And binary blobs, this is kind of binary blob that we're getting, and we can do nothing about that. And we don't like that, and we will fight with that as a coreboot community, and I believe this is something that we want to fix. And the problem for firmware consulting companies is time consuming to find the problems and fix the problems. And sometimes you can't do that because you just cannot work around the problem. So what kind of future work we can do with that? For sure, we need stabilization. We need merge in mainline. Those patches hanging quite a lot of time in mainline. There are not many reviewers, so if you want to contribute, feel free to do that. So we need to move these patches further. There are many advanced features, like you saw this register 64-bit register with advanced features. We have to think about if there is any value for that and maybe enable that. And maybe, I don't know, maybe GPU pass-through. I don't know if it's even possible, but it would be interesting. I wonder also if the same stuff is broken on Epic and Ryzen. And it's, I don't know, someone have to check that, because it's possible and this knowledge can be reused for new AMD processors. And of course, we have to prove that IOMMU protects against DMA attacks. And of course, if this will work, then next step is probably OpenXT or Viria OS or something like that. And to quote Joanna Rutkowska, we should go toward reasonable, secure, I don't know, routers. Okay, that's all from me. And thank you very much for, being here for so long. Now we can drink beer. Questions?
Don't know whether I got it right. Did you say that the firmware would be the more or less trusted environment, and the hypervisors or the Xen does not need to be trusted anymore?
No, that's I would say that doesn't mean that, but if you look at the projects which are made by kind of serious players in military, in air force, in automotive, they're going into that direction, and obviously they're using like hypervisors in embedded environment where you have kind of fixed set of virtual machines. Let's say your UI in your car got one virtual machine, but other virtual machine handling RTOS, which handles your, engine or brakes. So, and this all on Zen hypervisor. So I assume they know much better than me about the security and reliability of this solution. Of course, you are welcome to break it, but if you look at the history of Zen and how many times people were able to break through, it's not so often, and it's quite secure system, and that's why probably Joanna Rutkowska from CubesOS also working with Zen and trying to build on that. So I don't know.
Okay, so a second related question. So the firmware is configuring the IOMMU?
Yes.
Or is it done by both instances? Maybe Xen is doing it, and so the firmware is doing it in front of Xen.
So first of all, firmware is responsible, as I mentioned on one slide, firmware is responsible about exposing ACPI tables which say about the hardware configuration of the system. And IOMMU initialization have to be made by firmware, because if we're starting with hypervisor cannot handle that. But then using those features requires capability of the hypervisor and capability of the, if type 2 use it, capability of the system.
Okay, so the firmware is doing the basic initialization, and Xen is just using it then into the productive setting. Yes,
but okay. If we, for example, care about the DMA attack that may happen in between, while booting, that's why experts saying that you should do correct initialization as soon as possible, which probably is possible in maybe even in ROM stage, which is like, I don't know, like 100 milliseconds or less. So yeah, hopefully not enough time for performing anything. And if nothing is enabled, then there is no place to do the attack. So if PCI devices does not work, then there is no place to put the attack. Yeah, there.
Of course.
So we have to minimize the space where we can perform attack. The problem right now is there are two problems. We want to improve performance for Zen guests for this kind of platforms, and IOMMU have to work because didn't work previously, and have to have enabled advanced features because Zen using that and has correct support for that. And second thing is we want to if we have this virtualization, then we have to want to use these advanced virtualized operating systems like Viria OS or OpenXT. CubesOS in this case doesn't make sense because it doesn't have VGA output or any graphics. This is router system. So, but if something is based on AMD and use similar driver, then yeah, that also CubesOS.
Yeah, thank you.
Do you try to initialize the IOMMU without AGESA?
Without?
Without the vendor code, AGESA, AGESA?
We will not boot without AGESA. So.
Yeah, I only mean you can initialize the IOMMU with AGESA, right?
I'm not
without
using
it.
I'm not using like for IOMMU. Like I don't know what AGESA do inside, so I cannot do anything about that. But all the ACPI creation and the IOMMU driver is outside of AGESA. So I'm doing it in coreboot in open source way. So.
Thanks. Did you try to reach out to AMD about this problem? And if yes, what was your interaction with AMD on this? Because I think this is a very common problem with the GISA.
I think various developers tried to reach them about that many times and didn't succeed. So I just tried to do the work and not the talks. So it's like AMD. Like I have relation with AMD. I worked with them in different fields. But I know that it's for them, if there is not enough, I don't know, volume or not new platform or not something that will make a lot of noise around that, then they probably don't care. Okay.
Any more? All right.
Thank you very
Then
much.
thank you very much.